Quantum computing, harnessing the principles of quantum mechanics, is set to revolutionize fields such as medicine and machine learning by tackling problems too complex for classical computers. Quantum simulators, which consist of interacting quantum units, can be programmed to emulate intricate physical models, allowing scientists to extract valuable insights by controlling and measuring the interactions within these simulators. In a new paper published in Physical Review B, highlighted as an editor suggestion, a research team led by UC Riverside has introduced a chain of quantum magnetic objects known as spin centers. These spin centers, influenced by an external magnetic field, can simulate various magnetic phases of matter and the transitions between them. We are designing new devices that house the spin centers and can be used to simulate and learn about interesting physical phenomena that cannot be fully studied with classical computers, explained Sean Wen Tsai, a professor of physics and astronomy, who headed the research team. Spin centers in solid-state materials are localized quantum objects with great untapped potential for the design of new quantum simulators. Troy Lossy, Tsai's graduate student and the paper's first author, stated that these advancements could pave the way for more efficient methods of information storage and transfer, while also aiding in the development of room-temperature quantum computers. We have many ideas for how to make improvements to spin center-based quantum simulators compared to this initial proposed device, he added. Employing these new ideas and considering more complex arrangements of spin centers could help create quantum simulators that are easy to build and operate, while still being able to simulate novel and meaningful physics. Below, Tsai and Lossy provide further insights into their research. Q. What is a quantum simulator? Tsai. It is a device that exploits the unusual behaviors of quantum mechanics to simulate interesting physics that is too difficult for a regular computer to calculate. Unlike quantum computers that operate with qubits and universal gate operations, quantum simulators are individually designed to simulate/solve specific problems. By trading off universal programmability of quantum computers in favor of exploiting the richness of different quantum interactions and geometrical arrangements, quantum simulators may be easier to implement and provide new applications for quantum devices, which is relevant because quantum computers aren't yet universally useful. A spin center is a roughly atom-sized quantum magnetic object that can be placed in a crystal. It can store quantum information, communicate with other spin centers, and be controlled with lasers. Q. What are some applications of this work? Lossy. We can build the proposed quantum simulator to simulate exotic magnetic phases of matter and the phase transitions between them. These phase transitions are of great interest because at these transitions, the behaviors of very different systems become identical, which implies that there are underlying physical phenomena connecting these different systems. The techniques used to build this device can also be used for spin center-based quantum computers, which are a leading candidate for the development of room-temperature quantum computers, whereas most quantum computers require extremely cold temperatures to function. Furthermore, our device assumes that the spin centers are placed in a straight line, but it is possible to place the spin centers in up to three-dimensional arrangements. This could allow for the study of spin-based information devices that are more efficient than methods that are currently used by computers. As quantum simulators are easier to build and operate than quantum computers, we can currently use quantum simulators to solve certain problems that regular computers don't have the abilities to address, while we wait for quantum computers to become more refined. However, this doesn't mean that quantum simulators can be built without challenge, as we are just now getting close to being good enough at manipulating spin centers, growing pure crystals, and working at low temperatures to build the quantum simulator that we propose.